So it's about non-SUSY strings and the Swampland.
Yeah, thank you very much, Peter. And yeah, let me also start out by thanking Miguel, Irene, and Kumrun for organizing this wonderful short conference. It's really nice. I enjoyed the talk so far. And it's great that we can be together, at least virtually. So yeah, when we had the opportunity to split this talk with a younger collaborator, I happily seized that opportunity, and I will kind of provide a broad introduction, and then Niccolo will talk about all the interesting but ugly details. So the workshop is called Zooming In on the Swampland, and while Kumrun kind of came up with this idea of the Swampland already like 15, 16 years ago, and it was very exciting then, and people cared about it. It's fair to say that in the last couple of years, it has kind of exponentially grown and kind of subsumed pretty much everything. It seems, so everybody here worked on it and many more people, presumably. And it has incorporated like parts of mathematics, cosmology, and many other areas. So what I kind of want to zoom in first is string phenomenology. And for me personally, I'm convinced that the string phenomenology also incorporates our universe. So I've been lately just as a motivation kind of sometimes thinking about our universe. And there are, of course, these obvious big puzzles that in particular with the de Sitter Swampland conjecture now came back to the forefront. There are experiments going on testing inflation or something else. What is it? What kind of scalar potentials can arise? What could have happened in the early universe? And similarly, there is the issue with dark energy and quintessence that is currently being tested by observations. The bounds are being tightened. And the interesting question is, of course, whether we can say something from string theory, whether we can fix all the order one coefficients and agree on what models are possible and what not. However, there's also, and it was often like worked on in the string community, but it's maybe not as hip or exciting right now. Well, maybe, I don't know. It depends who you talk to. There's also the standard model of particles, and that used to be super exciting by the time the LHC turned on, and everybody had huge hopes. But now in the last 9 years, there hasn't been any discovery, and it seems highly unlikely that there will be at least a confirmed discovery of supersymmetry or something. So I pulled up, I saw this recent article. You have Higgs bosons everywhere, but there is no SUSY. So as I say, supersymmetry is facing reckoning. So it seems somewhat difficult or unlikely that supersymmetry, if it exists at all, will be discovered in the foreseeable future. And that is certainly true here for this particle physics, but if you think about it, these other two cases, there are obviously there's no SUSY in de Sitter space. So here, likewise, there is no supersymmetry. Similar for inflation, supersymmetry is nowhere. So supersymmetry is something we put in because it makes our life easier. I hate fermions. Most people might not like fermions like me. Bosons are just simpler to deal with, and the calculations are more under control. So it is great, but I mean, we also have to admit currently we have no experimental evidence for it. And we had hoped it solves the hierarchy problem, but that doesn't seem to be the case, and it certainly doesn't solve the cosmological constant problem. So that makes me think about non-supersymmetric string theory. And many attempts in string theory of trying to connect to our universe, they kind of start getting a 4-dimensional n=1 supergravity. We have some string theory in the back of the mind where we can calculate corrections, where we can see what is possible. But we kind of build a 4-dimensional n=1 theory, and then we try to build like a standard model from heterotic string theory, like E8 times E8, or intersecting D-brane models in type 2A or whatever, magnetized branes type 2B. You can put D-branes at singularities, F0 and Calabi-Yau 4. There are a gazillion of ways of how you can do that. And that's all very interesting and could be right and could be our universe eventually. But in principle, we have no evidence so far for this underlying SUSY that you have such a 4D n=1 supersymmetric theory. So I have been lately trying to think about more non-SUSY theories that are maybe more stringy. So instead of like getting something that people get from low energy effective field theories and see what constraints you have there. You can say, let's do something really stringy that is non-supersymmetric, that is somehow different from first constructing something for the n equals 1 or anything else. So one option that was explored a little bit lately, not by me, by other people in very interesting papers, is you can break SUSY at the compactification scale. That is very different from what low energy effective field theories usually are doing. I mean, so there was a paper by Quentin, Emilian, and Severin, for example. They compactified string theory on a non-supersymmetric space, kind of non-SUSY preserving space, and they studied which kind of swampland conjectures are still satisfied and how do things change. And there they actually did full string theory calculations. So it's very interesting. There are other papers by Bobby Acharya et al., where he asked how special are these special holonomy spaces we compactify string theory on, like Calabi-Yau's or SU3 structure, SU3 times SU3 structure, and so on. Are they really special, or is this somewhat more generic? Because if we don't do that, there are tachyons, there are other issues that come up. So this is definitely an interesting area of string theory that hasn't been explored all that much. However, this is not what I want to talk about here with Niccolo. So what we have been thinking about, and it also ties into a paper from Aaron from 2005, is either throw in some random string theory ingredients you would expect to get a SUSY breaking scale at the string scale. So in particular, if you put D-branes or something non-supersymmetric branes or branes in random configurations, you would expect the SUSY breaking scale to be at the string scale. Or the other case would be you could start with an actual string theory that does not have any supersymmetry at all. And then you can ask, what are the properties? And this was, for example, discussed in Aaron's paper, where he said there should be fermions, there should be something which resembles supersymmetry. And this is somewhat very similar to what we find, but I think I would sell it slightly differently, maybe. So let me start first with these D-branes. So the way I think about it is they seem to be behind a lot of like controversy. So while most people would be okay with some ADS vacuum, I mean, it's still up for debate, but if you have some kind of ADS vacuum, most people are okay. Once you add the anti-D3 brane, you get a de Sitter vacuum. Then all these swampland conjectures kick in, and the big debate is about, does KKLT really work? What about LVS? And so on and so forth. So this is really being debated, and at least part of the issue at some point was the anti-D3 brane. And when we looked at type 2A vacua, we found unstable, always unstable de Sitter vacua, but if you added an anti-D6 brane, you found suddenly it became stable. So with the refined de Sitter conjecture, unstable was okay, but once you have stable de Sitter vacua, then it is unclear whether they can exist. And all these constructions, of course, have issues that need to be worked out and that are not maybe fully under control. So we don't really know. But the kind of key thing for me was the anti-brane. So I just wanted to separate the anti-brane from everything else and just look at it in flat space. And I have to say here, there were also other papers recently by David Andriot and people in Uppsala where they found similar potentially stable solutions. But everything is not at necessarily large volume or weak string coupling. So these are not necessarily controlled. But it should kind of serve, at least for me, it served as a motivation to look at anti-branes. So anti-branes by themselves are fairly simple objects. We can just study them in string theory, you can study them in flat space, and we have full control. We can do the full string theory. If you just do flat space, you can solve the full string theory and you can learn a lot. And they also exhibit other interesting features. So I will mention a couple of basic features. So this is kind of an introduction, and then Niccolo goes into the details. And for them, supersymmetry is spontaneously broken, but it's broken at the string scale for anti-branes. So it's really like a stringy effect. It's a stringy object then, and it's very different from low energy SUSY breaking, for example. But the SUSY is non-linearly realized, and on this, like, there were a gazillion people. I wanted to cite some people at some point, but then this totally got out of control. I was going to see whether I get everybody in the alphabet, but I didn't find anybody with an X in his last name. So I gave up here and put ... But with Tuan van Poyen, Christoph Ruprecht, and Niccolo, we looked a little bit at antibranes and flux compactifications and in flat space, and this is kind of how I started to think about this. And here in particular, I just want to draw in my intro some basic picture. So if you just put an O-plane in flat space, then you have kind of a fixed orientation. And if you put parallel a D-brane, it just preserves the same supersymmetry. They are mutually supersymmetric, and there would be some kind of mirror O-plane, D-brane, sorry, but due to the O-plane projection. But now if you start rotating this, then you break SUSY because they are not parallel anymore, and the SUSY breaking is essentially determined by this angle. So what I want to tell you here is a very basic fact. If you have thought about this for a while or for a few minutes, you probably figure that out yourself already. If you rotate that around, it becomes an antibrane, and that antibrane corresponds essentially to the angle rotated by pi. That means if you keep rotating, it becomes a brane again. That means in this particular setup, there is a maximum SUSY breaking scale. So naively, maybe you would have thought, I can just send the SUSY scale to infinity. Like for low energy field theory, if the SUSY breaking is high, why can't it be as high as it wants? In this particular setup, with branes and these other stringy ingredients, it seems you cannot send it to infinity. You can send it at most to the string scale, and that is it. So this was one of the surprising facts that I didn't really appreciate before. So this particular setup, supersymmetry is spontaneously broken, and there's still some nonlinear realization. And one can ask whether something like this is true for other non-SUSY string theories. And I think the answer is no. All other questions I kind of writing here with a question mark. The answer should be yes, but for this one, I don't think it's generically true. So I think these anti-D branes, they are somewhat special compared to other non-supersymmetric string theories. But I'll say more about this in a second. However, there are another interesting feature. It's not only that the SUSY breaking scale is kind of bound. This anti-D brane has essentially the same spectrum. So there is a mirror anti-brane somewhere over here, but both contain bosons, fermions, essentially the same spectrum as a D brane. I just rotated slightly. The O-plane doesn't project out any fields. So if you calculate certain loop corrections or whatever not in these corrections to the Higgs mass or who knows what, you would expect a lot of cancellations because here are still the same. There's a gauge field living on there if you have transverse scalars and their corresponding fermions. So in this setup, given that you have bosons and fermions at potentially similar mass levels, you would expect a lot of miraculous kind of cancellations, at least miraculous from a low energy field theory point of view. What I want to do next, I actually put the anti-D brane on top of the O-plane. That projects out some degrees of freedoms. So this setup, I think it was shown by Angel Uranga in '99 and others, is perturbatively stable. The massless bosons, the bosons, for example, that move you left and right, they are projected out because there's a single brane now, kind of a half in the quotient space. It can't move off because there's no mirror under the orient-default. So there are no bosonic degrees of freedom, but the fermions are still there at the massless level. So this is somewhat similar to the standard model. You have a lot of fermions, they all contribute to the cosmological constant, but very few bosons. Here you have only fermions contributing to the cosmological constant. Why is it not infinite at one loop level? And this particular setup can, for example, arise at the bottom of the Klebanov-Strauss road. And a lot of people studied that, and we try to work out the action and the different couplings and those things. But for this talk, I will just really ask about flat space. So in this particular case, as I mentioned, there are 8 fermionic degrees of freedom at the massless level, but no bosons. There is a contribution to the tree level cosmological constant. There is a cosmological constant generated at 1 loop, 2 loop, and so on. But the question, the miracle, the weird thing you would ask if you're a field theorist, how can this possibly be finite? Because the field theory, you would just send your energy scale up to higher and higher energy scales, and this would just completely diverge. However, string theory is UV finite. So in string theory, somehow these contributions from the fermions at the massless level, they need to get canceled. So this is kind of the question, how can we get in string theory finite results, which need an infinite number of miraculous fine-tuning or cancellations when we don't have supersymmetry. And the answer is kind of in Niccolo's talk. As you will see there, fermions cancel against bosons at different levels. However, in order for that to work, you actually always need bosons and fermions. And in this particular case, you have kind of spontaneously broken SUSY, so maybe there's some variant of SUSY that somehow helps, but I don't think that is generically the case, but this is kind of what we try to understand. Is this really supersymmetry that is somehow broken that does this? And I don't think so, because there are also non-supersymmetric string theories. There are non-supersymmetric string theories that have no supersymmetry. They nevertheless give you finite answers. Many things like certain supertraces and so on, they actually vanish, although there is no supersymmetry at hand. So when you think about non-supersymmetric string theories, maybe the first thing that comes to mind to everybody is the bosonic string. The bosonic string only contains bosons. However, that one has a tachyon. So those theories, I would say they are no good. We don't really know a stable ground state or anything. So this theory, I wouldn't really consider as a good string theory, as a good theory of quantum gravity due to the tachyon. However, there are other theories that don't have any tachyons. For example, the SO16 times SO16 string, which is an orbifold of the SUSY string. There, via an orbifold, you project out all supersymmetry and you don't generate a tachyon. This is a tachyon-free theory. It has no supersymmetry, but it contains bosons and fermions. And the bosons and fermions, they appear in a very miraculous way. They appear in such a way that they kind of cancel themselves against each other, although they don't appear at the same mass level. And I believe something like this might be true in general. So I believe any kind of tachyon-free, and there are arguments by Clistinus in 1994 and so on, that essentially all non-supersymmetric string theories without tachyons seem to contain bosons and fermions. This is just required for finiteness. If you calculate something like the one loop cosmological constant, you essentially take bosons minus fermions. If you have only bosons, you get infinity. If you have only fermions, you get infinity. If you have bosons and fermions, then you can get the finite result you would expect from string theory. And there's a simple argument, as I said, by Clistinus in 1994 paper. And similarly, more involved, there is an argument by Aaron in this Swampland 2005 paper where he discusses fermions in detail. Also in his 1903 review, I think he discusses fermions. That is, however, much more involved. I mean, the finiteness argument is just if I calculate one loop, I can't have only bosons or only fermions. But it seems at least that all non-supersymmetric string theories contain bosons and fermions. The other thing, D-branes and other ingredients like this seem to have an upper bound on the SUSY breaking scale. So these are kind of the 2-3 takeaway messages if you have never thought about this much. So there are always bosons and fermions. Some ingredients have an upper bound on the SUSY breaking scale. Is that something one should expect? I have no idea, but it certainly seems to be true here. And if the SUSY breaking scale hits the string scale like for an anti-D-brane, then this is truly completely different from usual SUSY breaking, right? Because at the SUSY breaking scale, then the string tower comes in. So these are really SUSY ways of stringy ways of breaking supersymmetry. And yeah, lastly, those non-SUSY branes and the anti-D branes, they all have features very similar to each other, where bosons and fermions cancel in a very particular way. And the question is that coincidence, or is this a feature of all non-SUSY string theories? And I believe it's a feature of all non-SUSY string theories, and it has something to do with modular invariance, the conformal symmetry of the underlying string theory. And Niccolo will kind of elaborate on that now and provide a few more details.
Okay, can you see my screen?
Yes, we can.
Okay, so thanks, Timm, and thanks to the organizers for this opportunity. It's my pleasure to speak here. And I will continue along the discussion initiated by Timm. And in particular, I will try to give you a bit more details about this recent paper we have done in collaboration with Susha, Flavio, and Timm. So from Timm's talk, we've seen that the non-supersymmetric string theories are motivated for phenomenology. But the main question we have at present is actually a basic one. So we're trying to understand how it is possible and if it is possible to still get finite results without supersymmetry. So how to have control on the theory without supersymmetry. However, this is a Swampland workshop, so we'll try to phrase things a bit more from a Swampland perspective, so to motivate what I'm going to talk about. And I will start by asking actually what is the Swampland program telling us about these kind of theories. So to address this question, I will review briefly the main points, some of the main points of this paper by Rampalti last year, which was already introduced by Timm, in which is studying the role of fermions in the Swampland. So as Timm was saying, one of the main lessons we have from the bosonic strings is that we need fermions to avoid instabilities on the vacuum. So once we accept the idea that we do have fermions in our model, then we can apply Swampland techniques to fermions, so Swampland ideas to fermions. In particular, we can apply the so-called emergence proposal, which states that the infrared dynamic of some field, for example, a fermion, is actually generated because of the integration of a tower of massive states which live in the ultraviolet. So this is a general statement. However, when you're considering a fermion, then there is a nice feature observed by Palti, which is the fact that the tower you are integrating out to generate the kinetic term for this fermion, well, this tower has to be made up by bosons and fermions. It cannot contain only bosons. So this is one of the motivation why we are studying theories with both bosons and fermions, but yet we are not saying much about supersymmetry. Still, we have the presence of bosons and fermions, and in an infinite number of them, actually. The other observation made in the paper by Palti is that you can argue that actually the supersymmetry breaking scale should be somehow close to the mass scale of the tower. So I would say in the rest of the talk that the tower is almost supersymmetric in this sense that I expect the supersymmetry breaking scale to be closely related to the mass scale of the tower. So to recap, I have two main expectations from general Swampland ideas. So the presence of one or more tower of states with both bosons and fermions, and then the fact that this tower should be almost supersymmetric. And now I will show you in concrete string examples, non-supersymmetric string examples, how these ideas, these general ideas of the Swampland program are indeed realized. So I will consider two models for this talk, which were already introduced by Timm. One model is a closed string model, so it's the famous heterotic SO16 cross SO16 theory, which is maybe the prototype example of a non-supersymmetric but tachyonic-free string theory, closed string theory. And then I will also consider anti-branes on OP planes in type 2. These second class of models is usually called brane supersymmetry breaking. And in this class of models, you are breaking supersymmetry with extended objects, typically branes. And therefore, the best tool you have in your effective field theory is usually nonlinear supersymmetry to describe the breaking. So the point I would like to make is that these two models are different in principle. They don't have any clear common feature, but at least there is one particular aspect that is similar between them. And actually, it's very simple to understand this aspect just by looking at the spectrum. So the exercise I'm going to do now is to calculate and to show actually what is the spectrum of these two models. So if one computes the number of states per each energy level, then one obtains a plot similar to this. So here on the horizontal axis, I'm showing you the level, the energy level, the increasing energy level in the string states. And on the vertical axis, I'm plotting the number of states with some log scale. And a positive number means that I have more bosons than fermions, vice versa for a negative number. So for both the model I was introducing before, so for both the heterotic and the anti-de Bruijn plane system, you obtain a spectrum of this type. So clearly, this spectrum is not supersymmetric, because supersymmetry is the statement that I have the same number of bosons and fermions at each level. And it would correspond to the case in which I'm also filling these dots, which are not filled in the plot. So in the supersymmetric spectrum, I would obtain precisely a pairing between bosons and fermions at each level. What happens in this model is that it's like the spectrum is so-called misaligned. So the fermions and the bosons are not really paired, but there is a shift in their towers, in their mass levels. The result is that we have an increasing number of bosons and fermions at each level. So we have an oscillation between bosons and fermions, which is increasing. And actually, the shift will never disappear. So the shift is constant, is just 1 unit in n levels, and it will never disappear. You can continue all the way to infinity with this spectrum, and the shift will never disappear. So what we are seeing here is actually a realization of those general Swampland expectations. So we have a tower of states, both bosonic and fermionic, in which supersymmetry is not really present in the strict sense, but it's like we are very close to have supersymmetry, because we have a tiny shift which still is always there all the way up to the tower. So this property has been called misaligned or asymptotic supersymmetry, essentially because the spectrum is misaligned with respect to the really truly supersymmetric case. And it has been introduced first by Deans in this nice paper in 1994. Actually, in the work by Deans, he was considering only closed strings. So for example, the heterotic model. And I will explain you that now in the recent paper, we have extended the results by Deans also to open strings. Deans also studied more physical properties together with some other collaborators and many other people about this feature called misaligned supersymmetry. And the physical idea they had in mind is to use misaligned supersymmetry to explain why non-supersymmetric string theories are still able to give you finite answers. So for example, you can calculate the cosmological constant or some supertrace in cases without supersymmetries, and still you find a finite number. And then in this very nice series of papers, they are explaining you why, according to them, misaligned supersymmetry can be the reason underlying these a priori unexpected results. So this is the general framework I'm going to talk about, and now I'm going to give you a bit more details on how this machinery works and on what we have been doing in the paper. So the problem is a problem of counting. I want to count the number of states per each energy level. So it's a well-defined problem, and also the solution is well known. The number of states in the string theory partition function is encoded into these coefficients A, where n is the energy level and I is the sector. So I'm considering a generic partition function with different sectors. And I want to calculate these coefficients, which are the coefficients of the power series of the characters in the partition function. So this will tell me the number of bosons minus fermions at each energy level in each sector. These numbers, A, are given by the famous Hardy-Ramanujan-Rademacher formula. And actually, at leading order, the behavior is quite simple. So if you are at leading order in the formula and you compute things at large n, then there is an exponential growth in general for these coefficients. The exponential growth is governed by what is called the Hagedorn temperature. Actually, this is the inverse of the Hagedorn temperature. And you can think of this as of the central charge of the worldsheet CFT. So it's not really the central charge, there are numbers there, but you can think of this as a central charge. So now this is the general situation without further assumptions. But if you assume supersymmetry, then you are saying the very strong statement that each of these coefficients is actually 0 at each energy level, and also at leading order, but at any of the subleading orders in this Hardy-Ramanujan-Rademacher series. So the question is how things are working without this very strong assumption. And this was explained, so possibility to explain how things work was given by Deans in the paper on misaligned supersymmetry. And the idea is still to try to cancel bosons and fermions, even if they are mismatched, so even if the spectrum is misaligned. So to cancel bosons and fermions at different levels, of course, I cannot really work with the coefficient A n because they are misaligned, so I cannot sum them. So the first thing I have to do, according to Deans, is that I have to promote n to be continuous. So I define these functions now of n. Once I have these functions, which have the property that they restrict to the previous coefficients for integer n, then once I have these phi's, I just take the average over the sectors in a modular invariant way. So I compute the average of the phi's over the sectors, and I define what is called the sector average quantity. Again, in general, you expect this quantity to have an exponential behavior, which is now governed by some central charge, which I'm calling CF, so some effective central charge. So this again general, but if you do this calculation and you compute what is this value of the effective central charge, and if you find that the effective central charge is actually smaller than the maximal one, so than the Hagedorn central charge, then you can claim that your model is exhibiting misaligned supersymmetry. So if this condition is true, this means that some of the exponential behavior is canceling between bosons and fermions in your theory or between the sectors of your theory. So even if you're not really assuming supersymmetry, if for some other reason this cancellation is happening, then you can call your model to exhibit misaligned supersymmetry. So this is if you want somehow a definition or the smoking gun of misaligned supersymmetry. But actually, Deans took a step forward in his paper, and he conjectured that the effective central charge, if you do the full computation, including all orders in the Hardy-Ramanujan-Rademacher series, then the effective central charge should be 0. So if this conjecture is true, then this means that there is a huge amount of cancellations, in fact, between bosons and fermions at different levels, but at any order in the Hardy-Ramanujan-Rademacher series. And then this means that we are very close to the situation in which supersymmetry is indeed restored, because we don't have any exponential growth at all. We have a growth which is at most polynomial.
Niccolo, sorry to interrupt, but I have
Yes.
to say that time is essentially over.
Okay, so very briefly, I will just tell that we have extended this result in 2 ways. First of all, we consider also open strings, so the anti-brane system, and we discovered the presence of misaligned supersymmetry also in open strings. And then with an alternative Hardy-Ramanujan-Rademacher formula, we were able to prove that the conjecture by Deans is true. So in a subclass of systems, at least, we were able to prove that the conjecture that the effective central charge is 0 holds true in this class. Now, okay, now we are studying supertraces, but I don't have time to talk about this, so I will just conclude. From generic considerations in the Swampland program, we expect 2 facts, essentially, a tower, one or more towers with both bosons and fermions, in which we expect some SUSY restoration or almost SUSY restoration. And then the main point I wanted to show here is that string theory is realizing this in non-supersymmetric setups. Actually, we found that the same mechanism is at work in models which are different a priori, so closed strings and open strings. And now we are trying to understand how this feature can explain physical cancellation, for example, by calculating supertraces. So thank you.
Very good. Thank you very much, Timm and Niccolo, for your nice and clear presentation. There's time for questions. Let me see. We start, I think, with Miguel.
Yeah, thanks for a very nice talk. So So I have a question about what is your take on the SO16 and SO16, because you've been both Niccolo and Timm, you guys both have referred to it as a genuinely non-supersymmetric theory, but precisely because you have the level mismatch is just, you know, it's one level. If I go at energies far above the string scale, it looks supersymmetric, right? So even in, I'm just asking if you would agree that even for SO16 and SO16, you restore supersymmetry. There's some sort of supersymmetry, which is, you know, it's almost restored at energies far above the string scale.
Yeah, I mean, Niccolo and I had this discussion. My take, which is slightly different, which is maybe I want to sell string theory better. It seems you need for finiteness, which string theory has, bosons and fermions. And string theory arranges the bosons and fermions in a very particular way by kind of oscillating back and forth. That looks somewhat like supersymmetry, and it's called officially misaligned supersymmetry by Keith Dennett. But it is not clear to me that in general, there's any connection to supersymmetry. I would say this is a feature of string theory that is different from supersymmetry that guarantees finiteness. I could be wrong. I mean, this is something with Niccolo we were discussing. Is there now in the massless level maybe a gravitino or something? Can you somehow say? But the heterotic string we start with, the E8 by E8, has 16 supercharges. There were never 32. There are only 16. Those 16 we explicitly project out. It could be that there are hidden miraculous other 16 supercharges in the E8 times E8, but I doubt it. Why in the projected out, maybe suddenly 16 supercharges appear and we haven't found them that are broken or nonlinear. But yeah, I haven't seen it.
Right, but I was not thinking that you would see them in the IR. Like, I agree with you, there are no supercharges in the IR. But if it's kind of like an energy flow question, right? Like if you look at the theory, whereas the physics of the theory, how you model that energy scale is far above the string scale, then to me it looks very supersymmetric.
Yeah, I mean, it could be. I mean, I can write down a theory with supersymmetric broken that looks exactly like this. But the question is, how do I distinguish that from a string theory that forces that upon you by modular symmetry or modular invariance? I don't know. Yeah.
Thanks.
Yeah.
Irene, next question.
Yes, I actually have two questions, but so first I was wondering if misaligned supersymmetry could also work if the bosons are massless and then you start alternating instead of starting with massless fermions. Like, is there any reason why in the string theories we find the massless fermions? I mean, there are reasons based on anomalies, but I don't know. I was wondering if.
Well, not that I'm aware of, actually. I think it happens in these models, but I don't have an argument why it happens indeed. In the paper by Deans is constructing toy models in which you can have any possible starting point. So I don't know how much those are physical, but for what he calls misaligned supersymmetry, this is not a requirement to start with fermions. Okay.
And then there are these proposals that maybe there is a way to get the SO16 cross SO16 from a non-supersymmetric background of M theory, breaking a la sex bars, like that the strong, this dual, no, is related to an orbifold of type 0b. Do you have any comments about that? I mean, because that would be also a way to restore supersymmetry somehow.
Well, I don't know. Comments in which so you are asking if it is you expect to have misaligned supersymmetry to be present also in those models?
I think, is that by Keith, Dennett, and Bloom or something, a paper, or some other people where they kind of explore the moduli space at strong coupling and so on and use dualities, and then they find, I think, in one of the corners even something supersymmetric or so. But I don't have a deep understanding, or I don't know. I mean,
I think they propose that it can be understood, these non-supersymmetric string theories can be understood as some kind of Church-Schwartz reduction of M theory. And like what piece of evidence for this is that Church-Schwartz reduction is a little bit like it, because you think that you restore supersymmetry if you're much smaller than the circle, but you don't in string theory because there's winding strings going around a circle and they always feel supersymmetry. And if you make the circle very big, you never really restore supersymmetry in a full theory because the winding strings, the separation in the bosons and fermions in the winding string just keeps getting bigger. So it's just like misaligned supersymmetry. You have increasing splittings as you increase up to an infinite tower. So I think for this reason, one of the reasons why they propose that this should really be understood as some kind of Schwartz breaking of M theory. And it seems very similar physics. But I don't think it can prove it at the end, but it gives some evidence, some arguments of why it can also be understood in some way like that. Okay. That's just my comment, yeah.
Okay, yeah, thanks.
The next question is by Kumrun then.
Yes, thanks, very nice talk. So this is the question. I want to see if you agree with this argument to try to explain this equality of bosons and fermions. So it will not give you any kind of supersymmetry, but will explain why bosons and fermions are equal in number roughly. So so the one thing we don't know, suppose your theory admits one fermion. Well, if it admits at least one fermion, then the group is not SO, but spin group. So let me assume that the gravity theory has a spin group, not SO group. Okay, so that assumption I cannot prove. For example, bosonic string naively looks like it could be SO group, but could be that there are these branes there that could give you fermions and so on. So let me assume that the correct group is always spin group. If it is spin group, then you will always can construct big black holes which are spinning with spin J, and you can go with count the entropy of that black hole with spin J and say, okay, I change J to J plus a half. Huge black hole with spinning, and then you add the spin plus 1/2. And you ask how many states are there? Well, they're almost equal. Because of the Beckenstein-Hawking entropy, you can calculate it. Now, you say, okay, this is for huge, massive black holes. We're talking about, fundamental string state, which is beginning to look equal boson-fermion degeneracy. But, this kind of correspondence principle, like what Polchinski and Horowitz did, already shows that black hole states can behaving like, string state can behave like black hole states for suitable regional parameters. So then it will demystify the fact that the bosons and fermions should almost be equal. And it will agree with your picture, Tim, that it doesn't have to be supersymmetry. It just says they are equal in number. And there's no deep reason other than the black holes, as usual.
Yeah, I mean, it sounds very plausible. I haven't thought about that deeply, but yes, exactly. You find one kind of function that I mean, Niccolo just made this plot going up and down because that is nice to see the oscillation. But if you just count the number of states, there's one function which is kind of very similar to what you described, or exactly the same as a black hole, where you just go half a step up and up and up, and you always are on the same kind of trajectory. Yeah.
Okay, thanks.
Luis Ibanez would be the next one.
Hi. I have a question, and I think there is a difference between the SO16 and in the D-brane case, because in the first example, I think you get a runaway cosmological constant, and in the case of the anti-D-brane, I think I remember you get a three-level contribution from the tension, and then a negative contribution at one loop. So in that second case, you are driven to a strongly coupled limit, right? Not to a runaway. Or I do not remember correctly.
Well, yeah, I also don't remember. I would have to check the sign, but I think what you're saying is probably correct, that they potentially lead to different runaways. I don't know, Niccolo, do you remember the sign?
No, I think is in this paper by Uranga, but I don't remember. I think he's studying this situation there.
The second case goes like 1 minus g squared or something like that. So g squared, if it's dynamical, what it is, because there is a dilaton, then it is driven to negative.
Yes, might be, yes.
Right, I think we calculated this second time, just wrote in our paper also. I agree probably that it's negative, but I don't know right now from the top of my head, I remember, but yeah, it sounds correct. Yes. They are different. I mean, they're different on many levels. They just exhibit a similar oscillation. And I would suspect this kind of oscillation is a generic feature of any string theory without.
All right, so I see that also Emilian has one more question.
Just to comment a bit on the comment of Eran, indeed, you can do a Scherr-Schwarz in M theory, and there are some very old papers. including a paper I wrote with Antonelli Sagnotti. There was a field theory paper by Fabinger and Horava. And it's you break supersymmetry indeed in the 11th dimension. You have an SO16 times SO16 gauge group indeed, but at the massless level, the spectra on both sides are supersymmetric because you break supersymmetry perpendicular to the branes in this case. So when the branes are far away, it's essentially supersymmetric SO16 times SO16. And if you are very, very close, it becomes, you start to have tachyonic modes. So that's what I remember about this shared Schwarz in M-theory.
Thank you. Could you just tell me again that the first paper you said with Sagnotti?
Antonelli and Sagnotti 98 called the supersymmetry breaking in shared Schwarz in M-theory. My first paper, Antonelli and Sagnotti. And there's a paper a bit later by Fabinger and Horava, which is a field theory paper, which they understand why the shared Schwarz boundary condition flips the sign of the flips the chirality of the gravitino on one side, on the other side of these two boundaries. And this explains actually something which we found in the string model, which have actually this contains an orientifold and anti-orientifold actually from the string theory point of view, this configuration of shared Schwarz breaking in the orthogonal direction.
But supersymmetry is never fully restored in the massive spectrum because there's always winding modes that can wrap the shared Schwarz circle.
Yes, but they are heavier and heavier.
Yeah, they're heavier, but that's like misaligned supersymmetry. The splitting increases with the mass always. So the very heavy modes are very non-supersymmetric. So supersymmetry is never restored in EEVs. That's true for any shared Schwarz kind of thing when you have extended objects in a theory. That's what I was saying. Yeah.
Okay, yeah.
Okay, I think we have time for one more question at least. I see Joe. Was there anything?
Yeah. Hi. Also, I mean, thank you so much. This was a great talk. I was curious if is there like a way you could like a continuous deformation that you can do that would that would like restore supersymmetry in each of these cases? I mean, some of these things we're talking about, like the introduction of anti-D3 branes, but then there was like sort of that way in which you could rotate the D3 brane. And I was just curious, can all of these misaligned supersymmetry situations be obtained by some sort of like continuous deformation of a supersymmetric model?
I'm not sure. I mean, I guess this M-theory kind of construction we are discussing somehow vaguely relates this SO16, whether one can describe it as a continuous. Maybe it's continuous in the radius of the 11th dimension, but it's not. Yeah, I don't think you can. I don't know. I'm not totally sure what the answer is. This is a good question. I don't understand this M-theory, what was mentioned well enough to say whether there's a continuous limit when you somehow enlarge the M-theory radius or something. For the D-brane, it seems, at least in principle, unless you do some compactification or something, there is some connection to a SUSY thing. Yeah.
Thanks.
All right. Are there more questions? No more questions. So then we thank Timm and Niccolo again.